Hello, and welcome back to the next lecture in the Sustainable Aviation MOOC. My name is Irene Dedusi, and we met before in week 1 of this course. Today, we will look at aviation's atmospheric impacts. Specifically, we will look at climate effects as well as air quality effects associated with aviation activity. Let's first start by looking at aviation emissions. Aviation emissions form due to the combustion of jet fuel in the aircraft engines. In this sketch here, we're looking at emissions from a typical two-engine aircraft during a 1-hour flight carrying approximately 150 passengers. You can see that the chemical species highlighted in orange is what is emitted from the exhaust. In terms of mass, the majority of those emissions are carbon dioxide, or so-called CO2, and water vapor. The remaining emissions consist of nitrogen oxides, or NOx, sulfur oxides, or SOx, as well as carbon monoxide, hydrocarbons, and particulate matter, or soot. Even though these species constitute less than 0.5% of the exhaust, they're very important, as in addition to CO2 and water vapor, they also contribute to aviation's atmospheric impacts. Now, the way these emissions form differs between the different species. For example, for CO2 and water vapor, we can fairly accurately estimate them if we know how much fuel was burned. For other species, however, the problem is not as simple. For example, for NOx and carbon monoxide, the formation of those species is nonlinear. And beyond the fuel burn amount, to estimate this, we also need to know about the specific mode of operation of the engine. In other words, those emissions per unit of fuel that is burned differ between takeoff, cruise, and approach, for example. Now, because the formation of these pollutants is nonlinear, this means that there are in some cases trade-offs between the different emission species at the exhaust. Now, the emissions aspect is itself nonlinear. However, as we will shortly see in the following slides, the atmosphere is also a nonlinear system. Therefore, it is important to know where the aviation emissions are deposited within our atmosphere. So let's see where these emissions are deposited in from current aviation activity. Here, on the left-hand side, you can see how aviation fuel burn was distributed globally in the year of 2005. You can see that the majority of fuel burn is in the Northern Hemisphere, and you can clearly see patterns in Europe, North America, and Asia, as well as the main flight corridors. Now, since 2005, aviation activity has increased, so the picture from a more recent year would look a little different. On the right-hand side, you can see where the fuel burn is deposited vertically in our atmosphere. Around 10% of aviation fuel burn is used during the so-called landing and takeoff operations. This is aircraft operations that take place within the first 3,000 feet, or approximately 1 kilometer within close to the surface of the Earth. Around 90% of aviation fuel burn is emitted at higher altitudes, and as a result, the majority of aviation emissions are thus emitted also at those high altitudes. We discussed what the aviation emissions are and where they occur. So now, let's take a look at the atmospheric impacts these emissions have. And let's start with the climate impacts. In this schematic here, you can see an overview of the different ways aviation impacts the climate system. Emissions of CO2 and water vapor have a warming effect in the atmosphere. Condensation trails, or sometimes referred to as contrails, these are the thin cloud-like structures you see sometimes in the sky behind an aircraft. So those contrails, together with the cirrus they may form, also have a net or total warming effect. The same is the case for NOx and soot emissions. Sulfate aerosols, on the other hand, have a cooling effect. Now, these contributions involve a fairly large number of chemical, physical, and radiative processes in the global atmosphere. So, let's look at these contributions in a little bit more detail. Here, you can more specifically see the best estimates for the contributions of each individual component, as well as the associated uncertainties, and, in a way, the current level of scientific understanding of each. Overall, in this plot, a red bar indicates a warming effect, and a blue bar a cooling effect. If you're interested, I suggest you pause the video for a second and take a couple of minutes to read this figure in detail, as there's a lot of information on it. An important point that I would like to highlight here are the two rows at the bottom of the figure. These show the best estimates of the non-CO2 impacts at the top row, as well as the total impact, which of course also include the CO2 impacts. The main takeaway here is that both CO2 and non-CO2 impacts are important in aviation's climate impact. Now, let's switch gears a little bit and look at the second atmospheric effect, that of air quality, or sometimes referred to as air pollution. Effectively, we're still looking at the same atmosphere, this time from a different lens, and we're primarily interested in this case in the increases or changes in the concentrations of a variety of atmospheric species or constituents at the ground level, so near the Earth's surface where we live and where we breathe the air. There are two main chemical species associated with air quality: fine particulate matter and ozone. Aviation emissions, similarly to emissions from other energy and transportation sectors, are shown to alter the concentrations of these two pollutants at the ground level. Breathing in increased concentrations of these pollutants has been shown to lead to adverse human health impacts, eventually leading to an increased likelihood of early death. Now, let's look at these pollutants in more detail, and let's start with particulate matter. Particulate matter, and specifically fine particulate matter, or PM2.5, is a group of small particles or liquid droplets with a diameter of 2.5 micrometers or less. These are very small particles, they're about 1/20th of a human hair, and when inhaled, they can penetrate deep into human tissue and cause adverse human health impacts. NOx, SOx, and particulate emissions from aviation primarily lead to the formation of PM2.5. For the majority of this formation pathway, ammonia from the background, from other sources, is also needed. The second pollutant of interest here is ozone, and this is specifically fitting today, as when I'm recording this here at TU Delft, there is currently an ozone warning in the Netherlands. While ozone at high altitudes, the so-called ozone layer, protects life on the ground from harmful UV radiation, near-surface ozone is toxic, both to humans and to plants, because it oxidizes biological tissue. Ozone forms from NOx and hydrocarbon emissions, and those chemical reactions between the emission and the formation of ozone are nonlinear, and they depend on a variety of factors, including sunlight. Intuitively, it makes sense that aviation emissions that take place near the surface, such as those from landing and takeoff operations, contribute to air quality. And this is sometimes referred to as local air quality. Its impacts usually take place near or around airports, and then perhaps spread a little bit too. However, high-altitude emissions also contribute to ground-level impacts. This is due to various mixing and chemical processes in the atmosphere, as a result of which emissions deposited at 10 or 11 kilometers altitude lead to ground-level air quality impacts. Of course, those impacts do not necessarily take place around airports. It is important, and perhaps a little bit unfortunate from a mitigation perspective, that the air quality impacts of aviation emissions are nonlinear. This means that a unit of aviation emissions has different impacts depending on where it is emitted. This is because the formation of air quality species, or the formation of pollutants, sometimes depends on the background atmospheric composition. For example, as we discussed, how much ammonia is available in the atmosphere. What this means in practice is that we have to assess aviation's impact together those from other sectors. Now, as you've seen, the atmosphere is a fairly complicated system. And in studying those impacts, there's two aims that we have. The first aim is to improve our understanding. There is currently a lot of active research at the moment on improving this understanding of the underlying chemical and physical processes that take place between emission and the atmospheric impact that we're interested in. And to do this, to improve our understanding, there's two approaches. The first is to utilize atmospheric chemistry and transport models. These are complicated models that simulate the entire global atmosphere. And in those models, as you can see here in the video, we tracked the effects of an emission, a release from aviation. The second approach is that of measurements, or observations, or monitoring. There are various ways to do this. They range from low-cost sensors next to a runway, as shown here in the picture, to more expensive experiments of flying behind an aircraft, sampling the air in its wake, to also utilizing the increasing availability of satellite observations. While, of course, we care from a scientific perspective about understanding the underlying processes, we also care about mitigating aviation's environmental impacts. As a result, there is ongoing work in translating this understanding in a way that it is relevant for decision-making. For example, decisions in aircraft design that you've already heard about before. It is also important to keep an eye out for potential new impacts of radically new technologies that may differ substantially from current aircraft operations and current emissions. Finally, as you may have already figured out, as I've pointed to them a few times, there are a variety of trade-offs involved in aviation's environmental impacts. These trade-offs include emissions trade-offs at the engine level, trade-offs within the atmosphere, and then even trade-offs within the atmospheric effects of interest, climate and air quality. It is thus important in all our mitigation efforts that we keep those trade-offs in mind and we make well-informed decisions between them. So what are the key takeaways of this short lecture? Well, the first one is that when we're talking about aviation's atmospheric impacts, there's two effects we're talking about, that is climate impacts as well as air quality impacts. From a climate perspective, it's important to remember that both CO2 and non-CO2 impacts are important. From an air quality perspective, it's important to remember that both emissions during the landing and takeoff phases of operation, but also high-altitude emissions contribute to the formation of ground-level pollution. Finally, there's a variety of trade-offs in a variety of processes involved. And those trade-offs are to be considered and to be kept in mind when making the mitigation decisions.